During their research, scientists observed that some molecular structures found in nature could not be scientifically explained with the help of the existing understanding of atomic orbitals. Pauling introduced the concept of the hybridization of atomic orbitals to explain the existence of such molecules. During hybridization, atomic orbitals of slightly differing energies redistribute to form a new set of orbitals with equivalent energies. The number of hybridized orbitals formed is equal to the number of atomic orbitals participating in the process. These hybrid orbitals align themselves in space such that there is minimum repulsion between the electron pairs. Because of this, the bonds formed by hybrid orbitals are more stable as compared to those formed by pure atomic orbitals. The phenomenon of hybridization is observed in the atomic orbitals s, p and d. Their possible combinations are sp, sp2, sp3, sp3d and sp3d2. Now let's study each combination in detail. In sp hybridization, one s orbital combines with one p orbital to form two equivalent sp hybrid orbitals. The hybrid sp orbital shows 50% characteristics of the s orbital and 50% characteristics of the p orbital. The hybrid orbital has a large positive lobe and a very small negative lobe. The hybrid orbitals are oriented in opposite directions, forming an angle of 180 degrees with each other. During bond formation, they provide maximum overlapping areas, making the bonds stronger and giving the molecule its linear structure. Some compounds whose central atom displays sp hybridization are BeCl2 and C2H2. In sp2 hybridization, one s orbital combines with two p orbitals to form three equivalent sp2 hybrid orbitals. They have a trigonal planar arrangement, and the angle between two orbitals is 120 degrees. Some compounds whose central atom displays sp2 hybridization are BeCl3 and C2H4. In sp3 hybridization, one s orbital combines with all the three p orbitals to form four equivalent sp3 hybrid orbitals. Each hybrid sp3 orbital displays 25% s orbital characteristics and 75% p orbital characteristics. They have a tetrahedral arrangement, and the angle between two orbitals is 109.5 degrees. Some compounds whose central atom displays sp3 hybridization are CH4 and C2H6. The hybridization of elements containing d orbitals leads to three distinct hybridized shapes formed by the mixing of s, p and d orbitals. They are dsp2, sp3d and sp3d2. Of these, we will study sp3d and sp3d2 hybrid orbitals closely. The energy of 3d orbitals is not only comparable to 3s and 3p, but also comparable to 4s and 4p. Therefore, the hybridization of d orbitals either involves the 3s, 3p and 3d orbitals, or the 3d, 4s and 4p orbitals. In sp3d hybridization, one s orbital, 3p orbitals and one d orbital combine to form 5 sp3d hybrid orbitals of equivalent energy. They have a trigonal bipyramidal arrangement, which leads to the formation of two different sets of angles between orbitals. 3 of the hybrid orbitals lie in one plane, making an angle of 120 degrees with each other. This plane is called the equatorial plane, and the bonds formed by them are called equatorial bonds. The remaining two orbitals arrange themselves above and below the equatorial plane, forming an angle of 90 degrees with the orbitals on the equatorial plane. The bonds formed by these two orbitals are called axial bonds. The axial bonds are repulsed by the equatorial bonds, causing them to be longer and weaker than the equatorial bonds. Ultimately, this makes molecules with sp3d hybridization more reactive. The central atom, phosphorus, in the compound PCl5 displays sp3d hybridization. In sp3d2 hybridization, one s orbital, 3p orbitals and 2 d orbitals combine to form 6 sp3d2 hybrid orbitals of equivalent energy. They have an octahedral arrangement and a bond angle of 90 degrees between the orbitals. The central atom, sulfur, in the compound SF6 displays sp3d2 hybridization. Thus, we can observe that the phenomenon of hybridization explains the characteristic geometrical shapes of polyatomic molecules.